In this video, we're going to talk about conditional probability. So conditional probability means that we're trying to find the probability of an event given certain conditions are already true. So this is the conditional part, right? We know something has already happened or already is going to happen, and what's the probability of the follow-up event. So the notation that we use here, we're still using that capital P for probability. And we have the first event and then this vertical bar and the second event. And the way you would read this is the probability of A given B. So you can think of that vertical bar as saying given. So the probability that event A happens given that we already know B has happened. So for example, if we're drawing two cards from a deck of cards, we might ask, what's the probability that the second card we draw is an ace, given that the first card was a queen? So we draw one card out, it comes out a queen, we already know that that has happened. The next question is, all right, what's the probability that the next card is going to be an ace? Another example, if you flip a dime and a nickel, or you flip these two coins, we want to know the probability that the dime comes up heads, given that the nickel is already heads. So it might be that we flipped the nickel first, and then we're going to flip the dime, but conditional probabilities don't actually have to happen in order. So we might have flipped them at the same time, or we might have flipped the dime first. If you're thinking about this, you might notice that the probability that the dime comes up heads really doesn't matter what the nickel was. So the probability that a dime comes up heads, given that the nickel is heads, this is really just the probability that the dime is heads. And this quality is something that is pretty important in probability, so it has a name. So we've got a definition here. Events A and B are independent if one event happening has no effect on the probability of the other. So the example before where we were flipping a dime and a nickel, those were independent events because it really doesn't matter whether the nickel is heads or tails. The probability that the dime comes up heads is the same. So for example, if we roll two dice and observe the outcome, these two events should be independent. So imagine that the two dice we rolled were one was red and one was blue, just to tell them apart. So if I want to know the probability that we get a 6 rolled on the red die, given that there's a 4 on a blue die, well, because these two are independent, the probability of a 6 on a red die is going to be the same no matter what the blue die was. So these are independent. However, this next example, if you draw two cards in a row, like we were talking about before, these events will not be independent. So for example, suppose we're asking the probability that the second card is an ace. Well, if the first card that came up was a queen, the probability will be different than if the first card is an ace. So if you're playing blackjack, for example, the first card that comes up is an ace, the probability that the second card would be an ace is actually slightly lower. The reason being is that if you've already gotten an ace, there's only 3 aces left to draw from, whereas if the first card was a queen, there's still 4 aces left in the deck. So in this case, the second probability would be slightly lower. However, if we're drawing two cards from the deck with replacement, and I'm underlining these words, these terms are going to come up a fair amount in this section. With replacement just means that we draw one card, we look and see what it was, and then we put it back in the deck, right? We replace it, and then draw another card. Now in this case, if you're going to put the card back, then the probability of the next card, it doesn't matter what the first card was, so assuming we're shuffling all these cards. So drawing two cards with replacement would be an independent event. And drawing two cards in a row without replacement, this was dependent. One more example, if we're looking at the events rain today and rain tomorrow, to determine whether these are independent or not, I want to think about, what would we say about the probabilities here? If I want the probability that it's going to rain tomorrow, if it's given that it rained today, will the probability come out different than if it had not rained today? Well, probably yes. If it rained today, then that means that it's a little more likely that it'll rain tomorrow. It might not, but rainy days tend to come in groups. If it didn't rain today, probably we're in a season that is less likely to rain. So these are dependent. And we can determine this even if we don't know exactly what the probabilities would be for. We just have to think about, would there be any correlation between these two? And it doesn't have to be cause and effect. With drawing cards, it's clear that if we take some cards out, we can lower the probability of those cards coming up. But with the rain example, rain today doesn't mean that it's going to rain tomorrow. It also doesn't mean that it's not going to rain tomorrow. But if it rains today, we can say that there's probably a higher probability it will rain tomorrow. So when we're computing conditional probabilities, we really will use kind of the same methods that we've used before in computing probabilities, but we just have to think about what the condition is going to do, or what that given statement is going to affect. So in this case, we're looking at flipping 3 coins, and we want to find the probability that all 3 coins come up heads, given at least 2 are heads, so 2 or more. The way I would want to do this is think about, well, what are all the possibilities when you flip 3 coins? And we've gone through this before, listing out all the possible options for 3 coins. So go ahead and do that here. So before, when we did probabilities, say we just wanted the probability of 3 heads, we would just look at, well, how many ways can you get 3 heads? Well, that's just one way, out of the total. And if you list out all the possibilities here, there are 8 possible outcomes. But in this case, we're given that at least 2 are heads, which means that several of these possible outcomes are no longer possible. For example, we can't have 3 tails because not at least 2 of those are heads. So if we go through and eliminate any that wouldn't qualify for at least 2 heads, then we want to repeat, all of these ones would still be possible, and say, okay, how many ways can we get 3 heads? Well, this is still 1 out of, now there is a possible 4. So our probability here would be 1/4. Another example using some empirical probabilities, we've got this test result table again. So remember, this is patients who either have HIV or do not have HIV, and whether they tested positive or negative for HIV. So the first probability we have here is not a conditional probability. This is the probability that a subject has HIV. So if we look at the has HIV category, this is broken into 2 pieces, those who test positive and those who test negative. So this would be a total of 23 people with HIV. Now when you're doing probabilities with a table like this, I'd really recommend going through and making a total for your rows and columns, because it'll just make our computations easier. And remember to make sure that the total of your column and your row both come out, in this case to 1019. So the probability that 1 patient at random has HIV, well, there are 23 patients with HIV out of a total of, all the patients put together is 1019. And that would be our probability, or we could put that into a calculator and get the decimal. Similarly, the probability of having a positive test result, we just want to look at our total number of people with positive test results, which is 75, again out of the total. When we get to the conditional probabilities, again, we just have to interpret, what does this condition mean for us? So we're looking for the probability of a positive test result given that the person we've got has HIV. So this means that we need to look only at those patients who have HIV. So that would only be this column. The people who don't have HIV are not going to come into play here. So we're looking for the probability of a positive test result. Well, there were 22 people with positive test results in this group out of a total of 23. Or this would be about 95%. Similarly, this next one, we have the probability that the person does not have HIV given that we've got a positive test result. So in this case, we want to limit ourselves only to those who have positive test results. So that would be only people in this row. So we're looking for the number who don't have HIV. That was 53 in this group, out of the total, which was 75. And this comes out to about 70 or 71%. Now take a second to think about this. What this says is that if we know that the person got a positive test result, meaning they took the HIV test, it came out positive, the probability that they do not have HIV is 70%. So 70% of the time when you test positive for HIV, at least according to these numbers, you actually don't have it. This is called a false positive test result. And this very high probability here is what is sometimes referred to as the false positive paradox, because you'd think that if you test positive and it's a reliable test, which this one is fairly reliable, you notice that if you have HIV, the probability that you test positive was 95%. But because so many people don't have HIV in comparison to the population that does, we get these kind of skewed numbers. Okay, one more conditional probability here. Now we're saying what's the probability that the person has HIV given that they test negative. So again here we're looking only at the people who test negative. That's this 1 and 943. So the probability that they do have HIV, there's 1 out of a total of 944. This is of course going to be very small. We come out with about 0.11%, meaning that if you test negative for HIV, it's very unlikely that you actually do have it, although typically they want people to test more than once. Alright, so this is kind of the basic idea of computing conditional probabilities. Just make sure you first limit your options based upon whatever the given portion is, and then compute our probability as normal. So here's one for you to try. Again, we have a table of data here, and then there's a few probabilities for you to compute. This is about fatal traffic accidents and their relationship to age and cell phone usage. That's it for this video. See you next time.